Hello, this is the section 11.3 lesson. In 11.3 we're going to get another type of a hypothesis test, which at first glance may not look anything like what we saw in section 11.3, but the calculations are actually very similar, and this type of a hypothesis test has some very interesting applications. For this lesson you're going to need your calculator. First example, is the color of the motorcycle helmet somehow related to the risk of crash-related injuries? We might reason that if you're wearing a brighter colored helmet, you're going to be more visible to other drivers and less likely to get in a crash. Whereas if you're wearing a darker colored helmet, you're less visible and more likely to get into a crash. Seems reasonable. So to test this, we went out and collected some data. So we started off by observing 899 motorcyclists who were out riding on the street. And we're going to call those people not injured. Next, we looked at the records of 333 people that were either injured or killed while riding a motorcycle, and for each person we noted the color of their helmet. So we observed a total of 1,232 people. Out of those 899 that were not injured or killed, 491 wore black helmet, 377 wore white, and 31 wore yellow. Out of those who were injured or killed, 231 wore a black, 112 wore white, and 8 wore yellow or orange. So we observed a total of 704 people who wore a black helmet, 489 who wore white, and 39 who wore yellow or orange. Okay. Now this table here, without the columns labeled total, is what we call a contingency table. So the color of the helmet is what we call the column variable, and injured or not injured are what we call the row variables. Columns run up and down, rows run left and right. Okay. So the formal claim that we're going to test in this example is that being injured is independent of helmet color. Now that's, in the original question we didn't state a claim like this, but this is the claim that we're formally going to test in this example. So that's our claim, that they're independent. Well, let's set up our null and alternative hypotheses. If that's false, well then being injured is not independent of helmet color. In other words, they are dependent. The opposite of independent is dependent. Now our null hypothesis in this case is going to be the same as the original claim, just like in the previous section. Being injured is independent of helmet color, and the alternative is that they are dependent. Now in general, in this type of claim, the basic claim is that the row and column variables are independent. The null hypothesis is this claim, and this type of test is what we call a test of independence. So let's talk a little bit about the rationale behind the calculations. So we are, like before, we're going to start off by assuming that the null hypothesis is true. So we're going to assume that they're independent. So if they were independent, then the probability that I randomly select a person who is injured and wore a black helmet would be equal to the probability of being injured times the probability that the person wore a black helmet. Now this is true because independence and our multiplication rule says that if they're independent, then you just multiply the probabilities of my two events, like this. Well, I can calculate these two probabilities very easily. The probability of being injured is 333 divided by 1232, because I have 1,232 people total. Out of those, 333 of them were injured. The second probability is 704 divided by 1232. That's because, again, we have 1,232 people total, and out of them 704 wore a black helmet. Well, if I do that arithmetic, I have 0.154. So that's the probability that I randomly select a person who was injured and wore a black helmet. Well, now let's take this one step further. Again, assuming that they're independent, then the number of people that were injured and wore a black helmet would be equal to the probability of choosing someone who's injured and wore a black helmet times the total number of people in my sample, 1,232. So I take my probability of 0.154 times my sample size, and I get about 190. So if they really were independent, then I would expect to have about 190 people in my sample who were both injured and wore a black helmet. So I could do similar calculations for each one of these other categories. and I have this table of expected values. You see there at the column labeled black and the row labeled injured or killed, we have 190. That's where our calculation goes. We do similar calculations for all those other cells. So we have this table of expected values. Well, I also have this table of observed values. That comes from my data. And so, like in last section, we want to compare these expected values to the observed values. And just quickly glancing at them, there maybe doesn't appear to be a whole lot of difference between those expected values and the observed values. They're obviously not the same, but there's maybe not a whole lot of difference. But we want to measure the total difference and determine if it's significant or not. So we're going to measure that in the exact same way we did before. We're going to calculate a chi-square test statistic by taking each observed value minus the expected squared divided by the expected and then add them up. Now we're not going to do this by hand in this case. We're going to let the calculator do the work. These calculations get a little more complicated because calculating the expected values are a lot more difficult than the previous section. So the first step is we're going to enter the observed frequencies as a matrix. A matrix is simply a mathematical term for a table. And so to do that, we're going to go to the matrix menu, which you hit second X inverse. X inverse is on the left-hand side of the keypad, just above midpoint. And so second X inverse, and then select option edit, scroll over to the right, and then scroll down to option 1, which is matrix A. So see that on the left. Now don't forget to highlight edit. Oftentimes we just choose names and that won't do what we want. So choose edit and then choose option 1. Now once you choose option 1, hit enter and you'll get a screen that resembles that on the right. The first thing we have to do is enter the size of the matrix. We denote the size of a matrix by the number of rows times the number of columns. So in this case, my table of expected values has 2 rows and 3 columns. So hit 2 and then enter, and then 3 and then enter, and then that will take you down to the first cell of the matrix. And from there you just enter your expected value or your observed frequencies as they appeared in the contingency table. So hit 491 and then hit enter. That'll take you over to the next cell to the right. Hit 377 and then enter. Then 331, enter, and then that'll take you to the first column in the second row, and then enter the rest of the values as you see there. Now once you've entered your matrix, select Stat, Tests, and then option C, chi-squared test. Now every calculator should have this option. Now don't confuse this with the chi-squared goodness of fit option. This is a different test. So you see that option there in the upper left-hand screenshot. If you hit enter, you'll get a screen that resembles that right below it. And first thing you have to do is enter the matrix that contains the observed values. In this case, it's matrix A. That should be the default value. If it's not there, go back to the matrix menu and then under names, select the first option A and hit enter, and then it should paste A there. Now for the expected, we don't have to, the calculator is going to automatically calculate the expected values. We just need to know where you want to store them. We'll store them at matrix B, which should be the default value. Next we need to select either calculate or draw. Just hit calculate and you'll get a window that resembles that in the upper right. So in case chi-squared test, right below that we have our chi-squared test statistic. Right below that we have our p-value, and right below that we have our degrees of freedom. We could use that in the traditional method if we want. We're just going to do the p-value. So there's our p-value. Now if you go back to the matrix menu by selecting second X inverse under edit, select option 2B, you will see the matrix of expected values, which is automatically calculated. Notice the entry there on the lower left, 190, that's calculated the exact same way that we did on the previous slides. Now, this matrix isn't terribly important for our purposes, but that's what it means. Okay, so we calculated our p-value to be 0.012. Now we need to interpret this, and we'll do it in the exact same way that we've always done. We're going to compare that to our significance level alpha. None was given here, so we'll take it to be 0.05. Obviously the p-value is less than 0.05, and so we reject the null hypothesis. We're going to word the final conclusion in the same way. Does the original claim contain equality? Well, no. However, the claim and the null hypothesis were the same. So if we go down to no, notice it says original claim does not contain equality and becomes H1. Well, that's not the case either. So we're going to go to the right, yes. Do you reject it? Yes, we do. So there is sufficient evidence to warrant rejection of the claim that being injured and helmet color are independent. Okay. So we're rejecting the claim of independence. That means that they are dependent, which means that there appears to be some sort of an association between helmet color and motorcycle safety. Now, it does not mean that the color of the helmet causes you to get in crashes or prevents you from getting in crashes. It doesn't prove a cause and effect relationship. It just shows that there is a statistical relationship between the color of the helmet and being in a crash or not. Now, requirements for this test are very similar to the requirements from section 11.2. The data are randomly selected and are represented as frequency counts in a two-way table. Here our data has to be frequency counts, can't be measurements or anything like that. Number 2, the null hypothesis is the statement that the row and column variables are independent. That's always the form of the null hypothesis. And then third, each expected frequency is at least 5. Again, these are very similar to what we saw in section 11.2. Now our next example is going to be very similar to the first example, just a slight variation. When stores use scanners to check out items, are the error rates the same for regular priced items as they are for sale priced items? So to answer this question, we went out and we looked at about 400 regular priced items and about 400 sale priced items. The regular items, 20 were overcharges, 20 were undercharges, 15 were overcharges, and 384 were the correct price. Sale items, 7 were undercharges, 29 were overcharges, and about 364 were the correct price. So just what we have here is a contingency table. And just looking at the numbers, we see that of the sale items, we have a smaller proportion that are undercharges than we do for the regular items. And likewise for the sale items, we have a higher proportion of overcharges than we do for the regular items. So just glancing at the data, it looks like the answer to our question is no, but we want to formalize this a little bit more. So let's make a couple observations here. What we're doing is comparing two populations. We have all sale priced items and all regular priced items. What we have in our table is a sample from each one of those two populations. Every member of each of these populations has one of 3 different characteristics. They're either undercharges, overcharges, or correct prices. What we're testing is, what we're asking is, are the proportions of these characteristics the same in each of the populations? Okay. And so we're testing if these two populations have the same proportions of these characteristics. So this type of test that we're going to do here is what's called a test of homogeneity. Homo there means same. Homogeneity, of course, means that our two populations have are essentially the same in this respect. A test of homogeneity is really just a special type of independence. The calculations are the same. The only difference is how we word the claim. We're not going to use the word independence. We're word it slightly differently. Okay. So the way that we're going to word the claim, and which is the same as the null hypothesis, is that the two populations have the same proportions of the characteristics. Now this is a very, very generic way of wording our claim here, but wording it more formally using the words that was given in the original problem is kind of cumbersome. So this is our claim, which is the same as the null hypothesis. Now we're going to enter this in our calculator the exact same way we did the first example. Go to our matrix A, which again is second x inverse, edit matrix A. Now in this case our contingency table has 3 rows and 2 columns, so A is 3 by 2, and you enter it as you see there. And next we go to our stat test, a chi-squared test, Now you see our chi-squared value and our p-value. So our p-value is 0.0045, which is less than 0.05, so we would reject the null hypothesis. Now our final conclusion, we go to the right, and then do you reject it? Yes, we do. There is sufficient evidence to warrant rejection of the claim that the error rates are the same for regular priced items as they are for sale priced items. Okay. So the proportions of those characteristics in the different populations are not all the same. Now exactly where the difference is would take a little bit more analysis. But what we see is that our original conclusion we got by just glancing at the data appears to be correct. Those two populations are not the same in terms of these error rates. So that's it for this lesson. The Course Compass homework is titled Section 11.3.